Good evening, everyone. Myself Ajith, and today, along with my colleague Abdul, we will be presenting to you FANG-MPC. It's an MPC-based framework for privacy-preserving machine learning with active security. And it's a collaborative work with my colleagues from TII and from University of Bochum. So coming to the motivation, let's have a look at like the list of PPML frameworks, like privacy preserving machine learning frameworks, or in short PPML, in various settings. So you can see like two-party setting, there are a couple of works. Then there is two-party with a helper case, which is like similar to what Divya presented earlier, like there is a dealer. And then there is three-party honest majority, four-party, and even n-party. And there are like a lot of works in various settings, and it caters to various security notions like semi-honest, malicious, again within malicious security with abort, fairness, guaranteed output delivery, like that. So one of the problems that motivated us is first the reproducibility crisis. So if you know, like nowadays, most of these conferences are kind of like demanding that, okay, at least the applied conferences are demanding like you should present the code along with your paper, because there is no other way to validate your results. You cannot simply like put some results saying like, okay, this is this much better, like that. So one of the main problem is like this reproducibility crisis. So how we can reproduce these results and how we can have a fair comparison mechanism. So among these results, like among these papers, first of all, like this just represents a subset of the works. There are a lot of works in this domain of PPML. So most of these works don't have a open source implementation. And second thing, for those that has an implementation, most of them are just the prototype implementation. So in many cases, it suffices for a relative comparison, like you do like both the protocols in the same setting, you implement it and compare so that you will get the relative improvement. But the problem is it misses the actual details, like what are the hidden costs when it actually comes into practice. So that is what we are targeting in this work. And like I said, like this lack of this like common platform to compare all these protocols, that basically causes a problem of like fairness in comparison. Because there is one paper which has their own implementation and their own setup, and then there is another one which has a completely different setup. So the goal is a platform to support a variety of protocols. So that's the high level goal. And what we focus specifically is in the dishonest majority setting. So in dishonest majority setting, we allow all but one corruption. So if you have n parties, you can corrupt, an adversary can corrupt all the way up to n-1 parties. So that's represented by t less than n, where t is the number of corrupt parties and n is the number of total parties. And we focus on malicious, or also known as active security. So that's like the strongest form of security among all these protocols, where the corrupt parties can arbitrarily deviate from the protocol. And the question that we want to ask is privacy preserving machine learning practical in this particular domain? By this domain, I meant dishonest majority setting with malicious and active security. Because as you can see from this summary, like most of these works with malicious security falls into this honest majority category. But except this zone, rest of the all are like with semi-honest security. Coming to MPC frameworks, there are actually a lot of MPC frameworks, and this is like just a subset of them, and in which you have already seen like references to Crypten, then Microsoft ECPC, and this motion is by Encrypto Group here in TU Darmstadt, and MP Speeds is one well among them, and we have Scale Mamba, MP Toolkit, like that. Now we started with Scale Mamba as our baseline, and I want to justify why. So coming with like starting with the pros. So basically, Scale Mamba has a ready-to-use domain-specific language, and it supports several protocols. I think it's around 18 of them with active security, and it incorporates this work of HSS 17, which provides Boolean security evaluation with active security, and it is a robust architecture. Like I said, the design is like it can support various MPC protocols in the front end while having like a unified backend. Now coming to the cons of it. So Scale Mamba was designed as like a MPC software. It's like designed quite some time in the past, like around 2014, around that year. And at that time, this privacy preserving machine learning was not like that famous. It was not that hype. So it didn't consider these aspects. For instance, like consider a very large program. At that, if I remember correctly, the programs that were benchmarked at that time is like AES evaluation or some smaller circuits like that. But when it comes to very large programs, so like privacy preserving machine learning, where you have a really large model, the actual challenges kicks in. So for instance, the scale Mamba as such, it cannot compile large programs. And even like it cannot even process any program if the bytecode size is greater than 2/32. And coming to another missing feature is the no decoupled pre-processing phase. So basically in MPC, we have seen in the previous talks also, so we can mainly divide the protocol into two phases. One is the pre-processing phase where like we pre-compute some data, which is like input independent, and use it later to get a very fast online execution. So Scale Mamba doesn't support this pre-processing phase as a decoupled one. So basically if you execute a program, it will first do the pre-processing followed by the online in one shot. So you will not be able to like decouple that one in the Scale Mamba as such. And it has limited IO support. For instance, if you want a dedicated pre-processing phase, the question is like, okay, you do the pre-processing and where to store it. So you need some mechanism to store it, make it persistent so that you can use it later in the online phase. So Scale Mamba doesn't support that one. And again, these are like neither pros nor cons. Like coming to like viewing Scale Mamba as a tool for privacy preserving machine learning, it lacks these specialized ML libraries which we have seen in the previous talks, like convolution layers, folding layers. There are like so many such dedicated tasks related to machine learning. Then another question is like how easy is to deploy such a like large program in MPC using this framework. And unfortunately, Scale Mamba is no longer maintained. So they stopped their support in last year. And another one, which is like practical costs of HSS17. You have the HSS17 protocol, which is like I mentioned, like it's a Boolean circuit evaluation protocol. But when it comes to actually implementing that, there are like so many hidden things. For instance, it requires a garbling scheme. And with the support of pre-processing, how to basically move this garbling phase to the offline, and how to basically have like persistent choice bits across the executions and all. That Abdul will be like presenting in detail in his part. Now coming to our contribution, to summarize, it's like, okay, real world concepts in practice. We want to see like, okay, how actually these protocols works in practice. And say MPC based framework for PPML inference. So here as it's shown here, like you can consider like simply a client and model owner who want to carry out an inference task. So the model owner is in possession of the model and the client has an input and they want to evaluate this inference securely. So we have this framework, FANG-MPC framework acting in the middle, which is like the MPC inference engine. And it has a associated pre-processing material that is generated by the offline unit and that it uses to evaluate the engine. And then the result is secret shared among the client and model owner. And if they wish, like they can reconstruct among one of them. So just to recap the contributions again, like it has a dedicated and deployable pre-processing. For instance, it has support for field arithmetic with modulo P, where we pre-process bounded randomness, beaver triples, matrix triples, etc. And then over modulo 2, we have like support for offline garbling, DAR bits, these kind of primitives. Then another one is we have also added a support for pre-processing by a distinct set of dealers. And we'll talk in detail about this one later. But at a high level, it's using fully homomorphic encryption based matrix triple generation and beaver triple generation, which are like the state-of-the-art protocols in this domain. So using these techniques, you can generate this pre-processed materials like beaver triples and matrix triples very efficiently. So we have like added support for having it generated by a dedicated set of dealers. And then we pass it through a mechanism which will make it compatible to be used in another setting with another set of parties. So this is like the whole transformation, which I'll explain in later in one of the slides. And from the optimization side, we combine ReLU operation, which is one of the nonlinear operations, with truncation operation, which is much needed in the machine learning to handle these floating point values. We use fixed point arithmetic notations for that. And we added this specialized ML libraries like convolution, batch normalization, all these ones. And it has an open source implementation and it is available in this URL. And currently we support the inference of LayNet, ResNet 18 and VGG 16 at this point. Coming to the framework, I'll go through each module of the framework one after the other, and then we finally see the whole picture. So the first one is the dealer module. Like I said, it supports pre-processing by a distinct set of dealers. So currently, the dealer module has support to generate beaver and matrix triples, and we use the FHE-based scheme from this MG23, which is like Asia CCS 2023. And to achieve active security, we use the CKPOK, which is Zero Knowledge Proof of Knowledge from BCS 20. So these two are combined together to get active security for this generation of beaver and matrix triples. And selling these works is very hard. So if there is no theoretical contribution, actually we do. Because the FHE-based scheme from this MG23, they don't consider this CKPOKs for metrics, generation of matrix triples. So if for those guys who know about FHE schemes, there is always a parameter evaluation associated with it. You need to get the right parameters to get the efficient scheme. So when you combine MG23 with this BCS 20 technique, you need actually a fresh parameter evaluation, because the other parameter evaluation is an overlooked one, so which will result in inefficiency. So we have a fresh FHE-based parameter analysis on when combining these two techniques. And in the previous talk, there was like, okay, which are the future works? So we have the FGPA-based acceleration for this dealer module on the way. Now, the second module is a converter module. Like I said, we have this pre-processing done by a distinct set of dealers. And let's think of like, okay, we are doing a two-party based inference scheme for now. So we need a mechanism to transform the materials that are generated by this set of dealers. Let's say like, okay, there are 5 or 6 dealers that are generating this one to this two-party setting. So this converter module does exactly that job. So basically you can have as many dealers you want. And in the online setting, let's consider just simply like 2 parties. Now this converter module acts as the bridging unit that converts this pre-processed material from one type to the other one, which is compatible with this. And in the current version of FANG, how the correctness of these materials are generated. So we don't actually do a checking in the dealer's phase. We just let them generate the material, and it can be even incorrect material, but we use a MAC-based checking in the online phase, so that even if they process some incorrect materials, the cheating will be caught during the online verification. But of course, you can add the results from 2020 and all, where you have triple success service, where you even have like additional checks to enforce like the dealer's process materials are indeed correct. So you can add that very easily to the system. Now, apart from the dealer unit and converter module, we have a dedicated pre-processing unit which handles all the remaining pre-processed materials which are not covered by the dealer unit. So currently it supports the offline generation of garbled circuits, dabits, and even like any modulo P material. Like sometimes we need some values which are bounded by a particular range. So it supports that one. And it has flexible IO and DB connectivity. As I mentioned, like we need to store these pre-processed materials to some place so that we can later retrieve it for the online execution. And what next? We are in the process of incorporating function-dependent pre-processing to the scheme, because now this unit is a separate unit. So you can even do function-dependent pre-processing, where you do some pre-processing steps using the knowledge of the function also. So that can leverage more information and basically get more efficient online phase. And the fourth component is a storage support. So basically, this handles all the pre-processed materials that are being generated. So we added support for the storage in Scale Mamba, which was earlier having only limited to console access. So we added a controller-based IO, where you can basically choose between a file system and a database. So if you choose the database, it will go to a corresponding database. And currently we have support in MySQL 8.0, where we have like some structured tables where all these shares are being put for each of the parties, so that they can later retrieve from their corresponding database. And coming to the last component of FANG, it's the evaluation engine. So basically using all the materials that are generated so far, it performs the evaluation. And it already has, compared to Scale Mamba, it already incorporates the state-of-the-art private comparison protocols. And there is a technique where we parallelize comparisons with truncations for better efficiency. And as I mentioned, like there are specialized ML libraries for convolutional, fully connected layers, forwarding layers, standardization, batch normalization, etc. So the complete picture is this many modules, like I explained. So it starts from the dealer module, and the material will be converted to the corresponding online phase via the converter module. In addition, we have a pre-process unit. All these materials will be stored in the database using database or file system using storage support. And then they are loaded to memory during the evaluation, and then they are later used. So with this, I'll conclude my part, and I'll hand over to Abdel for the rest.
Hello. So I'm gonna be super quick, so you can go to the super nice tour after. I know I'm the last thing stopping you to go through that door, so I know the feeling. So what we are gonna do is that we're gonna put aside the overviews. We're gonna try to talk about two particular cases where we observe what you saw in the previous talk, right? Where systems really don't align well with cryptography, and how we are trying to bridge a little bit the space in between. So I'm gonna talk about offline garbling. Why I need to talk about offline garbling? It's because although this is a quite logical idea, if you think about it, when you have VMR based generalizations, it makes sense to put the garbling offline. There is no real constructions that implementations that do this at any level or any framework. And Scale Mamba had a long time ago decided to implement HSS 17. They do garbling online, in part because of their findings in 2018 that they want to preserve reactivity and how difficult it was to manage the choice bits that are needed for the instantiation of OT extensions. Okay, so why we decided to do it? Well, first of all, like reviewers really wanted this, and yeah, it was difficult to convince them that this actually was not out there. And second is to actually really see, because we talk all the time about how cool it is that we have this offline phase that's capable to do everything. Well, there are implications about an offline phase, right? You have to be able to store things efficiently. You have to be able to retrieve them efficiently, like generalizations like HSS 17. They really grow in size with the number of parties. So how does this actually look like in practice, right? So what did we do? We did the most obvious thing. We decided that we had to leverage the storage support that we had, move the garbling offline, and then store with every preprocessed material that is that depends on peerwise max, to also store them together with the choice bits that they were generated. And then, and only then, if the choice bits that are being used in the online phase, they coincide with the ones that are being retrieved from the database, then you can execute, and then you can use this preprocessed material. Okay, we do that for Davids, we do that for garbage circuits, and we measure how much time it actually takes to load this into memory and to store it and so forth. And the takeaway is that size actually matters a lot in this kind of setups. Okay, so I want to build a little bit on that. I know I don't have much time, so I'm gonna try to resume a bit. But why I would need garbage circuits at all? Well, if you think about it, on PPML applications, truncations are one of the biggest bottlenecks. We have heard lots of talks today about how we actually try to circumvent problems like that. And now we have a huge infrastructure behind to actually support the dealer's model. How can actually leverage that to actually achieve some improvements on the evaluation of ReLUs, okay? While at the same time trying to get rid of all the cost of the truncation, okay? So what we did is to actually use the probabilistic truncation from Katrina and Saxena, like executed it at the same time as the comparison that is the base of the ReLUs that we use from Katrina and the Hawk. And what we did was to replace the Boolean evaluation circuit there for the garbling of line that you saw in the previous slide, and we measure all the stuff that you saw before. So to achieve that, you have to build the randomness in a weird way. I'm not gonna give much details on that, but all of this was stored and persisted, and we have special instructions to actually retrieve it from the databases. The takeaway is that there is an R prime there. That R prime there is constructed from a bit composition that is based on Davids. And then how you operate is that you do all your multiplications, you forget about your truncations. When you get to a point just before of the activation layer, you say, oh, now I need my truncations. Well, you use the mask that you construct, you add that to your last secret, and you open, okay? And the simple observation that many people has made actually in the past is that, okay, this C that is open is the same that can be used for the probabilistic truncation and for the comparison. And these two are independent, and well, I can basically reuse it, okay? So you can execute both at the same time. The takeaway is the red box there, that R prime is actually the bit composition on that uses Davids there, and that's a Boolean evaluation of a comparison circuit in between a public input and a secret input. And you can use offline garbling for that. So the garbling doesn't happen online, happens offline. Everything is optimized using this preprocessed material, and like it's not into memory before all of this even starts. Okay? So we have some cool benchmarking results. As Ajith said, this is one of the first setups that actually leverages active security over fields using common MPC frameworks, MPC protocols. So we benchmark these three, okay? And these are our setups. Sorry, I'm rushing, but we don't have much time. And these are a bit of our timings. These timings are preliminary. There is still lots of work to do that can accelerate this even further. We are able now to execute with active security on these platforms only the online phase with a real dealer's implementation, linear in between machines that have a quite fast ping distance in 20 seconds. And it can be further accelerated if we see that box there. The problem now that we have and that Scale Mamba had in the past is that the evaluation of garbage circuits happens one after the other. So we plan to actually be able to parallelize them. Once you do that, this time should be much, much faster. Okay? So this is what we have done. This is what we want to do in the future. We are looking forward to have some functional secret sharing somewhere there. We are quite excited about function-dependent preprocessing and this parallelization of garbage circuits. And this is all that we did. Like, you can read the paper and find out. Don't worry. And if you want to read the paper, that's the link. And that's the link to the repo. And thank you so much. Now you can go have dinner, have fun in the sun, and like, goodbye. Thank you.